2.4 is library functions and piecewise functions. So these first two slides are what we call parent functions, or functions before any transformations have been put in place. So you might want to pause the video and write these down. You also might want to have your graphing calculator or Desmos out and graph these as you go so you can kind of get an idea of what they look like better than my little sketches. So we have a linear function, that's a line. A constant function is just a horizontal line. This can be any value, this is just a number. Square function, which we usually call quadratic, that's our parabola. The next set, here's the next four. So again, you might want to pause the video, write them down, sketch them out first. So the first one we have here is a cube function, or a cubic function x cubed. So it looks like that. Square root function is only in the positive, or at least the parent function is only in the first quadrant. The reciprocal function, which we usually call a rational function, that's 1 over x. It has asymptotes at the x and y axis, so x equals 0 and y equals 0, and then is in the first quadrant and the third quadrant. And then the last one is the absolute value of x, and that's solely in the first and second quadrants because y's can only be positive for the parent functions. So the last thing we're going to talk about are piecewise functions. So what a lot of people don't realize is that absolute value functions are actually piecewise functions. So if you're taking the absolute value of x, if you have a positive x value, anything greater than or equal to 0, then whatever you plug in for x is just what you're going to get back out. So it's really just the line y equals x. However, when you're less than 0, when you're negative, whatever you plug in for x, you're going to get the opposite out. So it's going to match the function y equals negative x. So that is how you get an absolute value. So if you graph this, for all our x's positive, so over on the positive x-axis, you're just going to have the line y equals x. For all your next x is negative, you're going to have the line y equals negative x, and that's what creates this v of the absolute value. So that's just kind of the absolute value. When we go down to something like this one down here, f of x is equal to this whole piecewise function. And this is just something that has been defined. It's not a specific function like absolute value of x. It's just a defined function. So the first thing asks you to find f of 0, f of 1, and f of 2. So I want you to pause the video, look at the domains. So for those of you who haven't worked with piecewise functions before, this over here is defining the function, and this is telling you how that function is defined. So it's defined between -1 up to 1, and then once you get to 1, you jump to a different function, a different y for x equals 1, and then once you get above that, you jump to a different type of function for x is greater than 1. So look, using these domains, find f of 0, f of 1, and f of 2. So when you go to find f of 0, you need to find which domain set 0 exists in. The only one where 0 as an x value exists is in this first top part. It says between -1 and 1. So this is the only place that 0 as an x exists. So if you want to find f of 0, you go to this place, so you plug it into this part of the function. So f of 0 is equal to -0 plus 1, which is just a 1. For the second one, f of 1, you got to find the place that the x coordinate 1 exists. You have a 1 here, but it's not nor equal to, so it doesn't exist in this part. Right here it says when x equals 1. So when x equals 1, y equals 2. So you use this part of the function. So f of 1 is equal to 2. And the last part, f of 2, you got to find the part of the function where x equals 2 exists. This is where x's are greater than 1, so this is where the x coordinate 2 exists. So plug it in here, 2 squared, f of 2 is 4. So those 3 points. The next part, we want to find the domain of f. So when you're finding the domain of a piecewise function, again, you want to look at the domain breakdown on this side. So I always start at the smallest part. So real quick, what I want you to do is pause the video and try and figure out what the domain of this function, the total domain of the entire function f of x would be. So if you're looking at this, I always look over here at our x values. Our smallest x value that you ever reach. Usually the smallest x's are at the top and then you go bigger as you go down. So the smallest x coordinate you ever reach is a -1. So if I'm doing the domain, I'll do it right here. So if I'm doing the domain, okay, the smallest x coordinate I ever reach is a -1. Then I go all the way up to 1, but I don't include 1. But then down here I do include 1. I jump down to the next, it says, okay, now do include 1. And then I want to include everything bigger than 1. So I start at -1, I go up to 1, I include 1, and then everything bigger. So my domain are all the x's that are greater than or equal to -1. If we want to write that in set notation, we want to start at -1, we want to include it so it's a bracket. Sorry, that is set notation. If we want to write it in interval notation, we want to include it so it's a bracket, and we want to go all the way up to infinity. Infinities always have a parenthesis because you can't ever reach infinity. So the total domain of the function is x is greater than or equal to -1, or if you write it in interval notation. So now we want to graph it. So basically what I do is I graph each part of this function. So if we want to graph this first part, we want to graph the line -x plus 1, but only between x is -1 and +1. So I'm going to have a y-intercept of 1 and then a -1 slope. So at -1 it's going to be up here at +2, and then at +1, because I don't want to actually include x equals +1 in this part of the function, I'm going to have to do an open circle. That's how we say that we don't include it. So this is the first part of the function, that line y equals -x plus 1, but only between -1 and 1. So then the second part says when x is 1, y is 2. That's just a point. When x is 1, y is 2. So it's just the point 1, 2. So 1, 2, make a point. Then the last part says for all the x's greater than 1, the function behaves like y equals x squared. So starting at x equals 1, we want it to look like the function x squared. We don't want to include x equals 1 in our parabola because there's no or equal to. If we had an or equal to, it wouldn't be a function then. So I'm going to put an open circle on 1, 1, and then from there on, it just looks like the parabola y equals x squared. So I have a point at 2, 4, and a point at 3, 9. So it's going to look like this. So this whole thing is the function f of x. You have the first part in red, this line. The second part is just this blue point, and then the third part is the purple parabola. But the entire thing makes up the function y equals f of x. The last part of the question asks for the range. The easiest way to do range is with looking at the graph. So if we look at the graph, what is the lowest y value we ever reach? Well, right here we get really close. We have nothing negative. We get really close to 0, but we don't actually include 0 because we have an open circle right here. So we never actually reach 0, but our y's start at 0. Once they start at 0, so if we do it in set notation, we don't want to include 0, interval notation. And then from here, we have everything up to 2. We're included at 2, and then everything up above there. We have an arrow here, so it goes on forever. So everything greater than 0 is our range. So if we write it in set notation, y such that y is greater than 0. If you write it in interval notation, from 0 to infinity with parentheses on both sides. So here's our range.